My name is Melissa Darr, and I'm a water engineer with Arcadis. And what led me here today is that I'm also the leader of our sustainability community of practice, which is a cross-business line knowledge sharing and client development group. So through that, I've worked with our buildings division and sort of worked in everything we do related to sustainability. So who here has heard of the Water Energy Nexus before? Okay, we got a couple. If you haven't heard of it, you're actually not behind because there is no formal definition. You won't find it in the dictionary or anything like that. Everybody who uses the term has a slight variation of it, but in general, it refers to the interdependencies between the water system and the energy system. So this graphic shows us some of those. You can see, obviously, water is used for hydroelectric generation, but it's also used for cooling in thermoelectric generation. It's used up here for mining fuels. And then energy is used to pump that water to its users, whether in the city or in residential areas, and also to power the water and wastewater treatment plants. On the water side of things, energy availability is pretty vital to get the water where it needs to be and in the condition that we can use it in. So nationally, water systems consume 3% of all energy in America, and that comes out to 75 terawatt hours per year. And depending on where you are, that portion can be a lot higher or lower. So I'm going to take California as an example right now. In California, the California Water Project and the Central Valley Project combined form the largest water system in the world. And they pump water from the relatively wetter north to the Central Valley that's very heavy in agriculture and the densely populated south. And in the process, they have to pump water over 2,000 feet of elevation to pass the Tehachapi mountain range. 2001 happens to be the year that I have numbers for. In 2001, this system used 5 terawatt hours of electricity, which was 19% of the state's total electricity use. And this makes it the largest energy user in the entire state. On the energy side of things, constraints in water can challenge the reliability of existing systems, and they can also jeopardize the physical, economic, and environmental viability of future projects. If water is not available where a project is located, that project just cannot run. So this is important because under standard conditions, so this map shows if we get as much rainfall as we expect to get annually, just based off population growth and growth in demand, 40 states expect water shortages in the next 10 years. And this was from 2013, so some things have changed since then. As you can see on this map, Alabama is one of the few states that predicted no water shortages. But if you've been there in the last year, that was not the case. We're not always lucky enough to get average water conditions. So if we end up with a drought, the condition is even worse than what this map shows in terms of water availability. When I talk about water, there's 2 different types of water use that I'll talk about. Water withdrawals are any amount of water that is removed from a source, and water consumption is water removed from a source that is not returned to the source. So water withdrawals encompass water consumption, but it also encompasses things like cooling water that's taken out of a river or lake and pumped through a system, then put back in. When we look at just water withdrawals, the energy system consumes more water than any other use in America. When we're looking at water consumption, agriculture becomes the winner there. But both metrics are important because if you need water for cooling and it's not available, or if the cooling water requirement is all the water that a river has flowing at a given time, that's just not going to work out. This table shows us the gallons per megawatt hour produced for some standard electric generating technologies. And on average, throughout the country, about 25 gallons of water are withdrawn for each kilowatt hour. So I'm switching units, but now I'm talking about kilowatt hours. So consumption is far less than withdrawal, since most of this water is used for cooling purposes. And when we're using water for cooling purposes, most consumption happens through evaporation. So on average across the country, about 2 gallons per kilowatt hour are consumed by the time electricity reaches the endpoint of use. However, that's location dependent. And if you are in a hot area or a dry climate, it can be a lot more. So in Arizona, where I live, 7.85 gallons of water are consumed for every kilowatt hour produced. And we use a lot of energy in Arizona for air conditioning. So that's one of the problems with the energy water nexus, is that oftentimes water isn't abundantly available at the places where it's needed most. So in Arizona, obviously, it's very dry, and that makes us need more water for outdoor uses, but also lose more through our energy system. And it means that we need to be even more careful about how we use this resource. Another thing to note on this slide, as you can see right here, these technologies that have carbon capture and storage actually use about twice as much water as their more traditional counterparts. So obviously we want to conserve emissions where we can and cut back on carbon dioxide, but we need to be mindful of the other effects that these technologies have. And this is true for some other new technologies such as biofuels or fracking. These allow us more energy that wasn't available in the past, but they use massive amounts of water. And then through the water cycle, I've already mentioned a bit that water is used to extract water from its source and convey it to a treatment plant. We need energy to treat the water. We need more energy to pump it to its endpoint of use, to heat it or treat it again where it's used, and then to collect and treat wastewater. All of this uses a lot of energy. So how much energy is required varies depending on the treatment method. For example, let's say we're in an agricultural area that's just pumping groundwater and no treatment's needed, that's going to be pretty efficient in terms of energy use, but desalinating water right now is the most energy intensive water treatment method, and the theoretical minimum energy needed for that is 3.8 kilowatt hours per 1,000 gallons. So if we bring things down to the facility level, where most people in this room probably work, there's this conception or general perception that water is cheap. You might see your water bill and your sewer bill and think that's the end of the story, but there's actually a lot more to it. There's oftentimes on-site water treatment if this is a manufacturing process. There's labor to maintain that water treatment. There's water losses, pumping requirements within a facility, on-site wastewater treatment. You might pay more for off-site disposal depending on the quality of the water leaving your site. So lots more things factor into it. This breaks things down a little bit more. So on the water supply side, you obviously need to purchase your water from the city or the water company that you use. There might be pumping costs to get the water from where it is delivered to where it's needed within the facility. On the water purification side, you have electricity, maintenance, chemicals, labor, depreciation. Then this last one, water waste. I think it's important to note that if you're using a treatment such as reverse osmosis, the reject water could be anywhere from 25 to 75% of the total water coming into that system. So you might have 1,000 gallons coming in, but you can only actually use 250 gallons. Manufacturing uses, the main cost here is actually heating. Heating water takes a lot of energy, and because of heating requirements, the endpoint uses for water is actually the most energy intensive part of the water cycle. On-site wastewater treatment is similar to on-site water purification, but there might be added costs for analytics that are required to prove that the water was treated to acceptable standards to be released into the environment or sent to a city wastewater treatment plant. And then for wastewater disposal, you have your sewer bill, but there might be additional costs if some of your product or wastewater cannot be sent to the city wastewater treatment plant. You're going to have to pay somebody else to come in and collect that water and treat it for you. So if you take all these together, you can calculate the total cost of water at your site. This is a kind of long equation, but the ADA terms here are efficiencies, and then we have the costs of each system. So if we add them all together, this gives us the total cost. So a quick example here. This is something that one of my coworkers actually worked on. So it was a rinsing operation in a facility. They needed high quality water, so they were deionizing and using reverse osmosis. And they also need this water to be pretty hot. So there were costs for water purification and for heating. And then they had on-site wastewater treatment as well. So they had an idea that would reverse the total water use by 1 million gallons per year, and it was going to cost $30,000. This particular site had a requirement that the return on investment for any capital project had to be less than 2 years, which is a pretty quick time frame. So if we're just looking at, the standard perceived cost of water, we can calculate what the water bill and sewer bill would be, and we get this total cost savings of $5,540 per year, which could never get us to that $30,000 investment in 2 years. But if we expand the equation and look at some of our other costs, we can realize that water purification costs were $250 per 1,000 gallons, heating costs was another $350 in energy, and on-site wastewater treatment was costing us $590 per 1,000 gallons. So this all adds up to a total savings of over $17,000 per year, which helps us get to the $30,000 within 2 years. So when we do the return on investment costs or calculations, we can see that the expanded equation easily gets us the savings necessary to justify this investment, but just looking at water and sewer bills doesn't get us there because it doesn't tell the full story. So the problem that we're facing is lots of companies are facing pressure to reduce their water use, and they have sustainability goals where, as a company, they're saying they want to improve these processes, save energy, save water, and do better by the environment. But traditional water audits can fail to identify some cost-effective ways to save water and energy at the site. Lots of times processes focus on the end-of-pipe uses, so we'll do things like put in low-flow toilets or recycle rainwater. Those are great initiatives, but they might not be the most cost-effective ways to save water at the site. We need to make sure that our return on investment calculations actually tell the full story and capture all the costs that are going to be saved through any projects we do. And we need to make sure that we have complete information about all of our processes. So this leads us to the Water Kaizen Blitz, which I'm going to describe as a method for finding and justifying water-saving investments at a site. So Kaizen is a Japanese term that directly translates to break for the better. A more Americanized translation that lots of people use is just continual improvement. So some people in this room are probably much more familiar with lean manufacturing and Six Sigma than I am myself, but I'm gonna do my best to explain it now. Lean manufacturing is basically the concept of reducing waste in order to make processes more efficient and cost-effective. So Kaizen Blitz are different from Six Sigma because they have a shorter time frame. They're not meant to be long-term comprehensive plans, but rather they're a series of deliberate, planned, and easily implemented steps that lead to lean operations. A Kaizen event has 3 rules. All of the resources for the event should be immediately available. All actions should be simple and direct, and the event needs to be held on a tight schedule, so typically less than a week. Using this method allows somebody like a consultant to come into a site and quickly assess opportunities for savings and work with that site to maximize their return on investment for any improvements that come out of the process. So the timeline for one of these events has 4 steps. We're gonna do some preparation ahead of time because everything in life requires preparation. And then a water balance is essential to identifying opportunities where we could have savings. So that is something that you want to have done before the event begins. Then the Water Kaizen Blitz event itself takes place over 2 to 3 days. And this is where you're going to go to your facility and look for any low-hanging fruit where you could save lots of water and in the process save energy and other costs at the site. And then after the event, we'll sort of document our findings and talk to the proper stakeholders to get buy-in from everybody. So first of all, the pre-Water Kaizen Blitz steps are that you want to develop a schedule, gather background information and data. So if any water balances have been performed in the past, or if there's knowledge about any inefficient systems at the site, you should hear about that. And then you want to develop your team. One important thing for these events is that you want your team to be pretty diverse, because that will expose you to ideas that you wouldn't find, say, if you just had strictly a water person like me come in. You need facilities managers and people who work directly with the equipment to know sort of where opportunities are. So some helpful tools for a Water Kaizen Blitz event are pretty much anything that you would use on a normal site visit to assess the conditions. So if you have access to a flow meter, that's ideal. If you don't, a bucket and stopwatch could suffice for certain processes. Thermometers can help you understand which processes may be running hotter than they need to be. Then typical things, tape measure, flashlight, camera, PPE. You want to have a facilities manager with you who can give you access to any areas at the site that you need to see. So then for the water balance, you need to create a list of every process at the site that uses water, and you want to evaluate any existing data from water meters, process flow diagrams, or prior water studies. You should identify data gaps, because these are the things you're going to need to go back for and collect some more data. And you should perform flow metering throughout the site, then create your water balance. So this is hard to see, but you don't need to read everything. On this slide, each box represents a water using process. So this was developed for an automotive site, and these were all of the processes at the car manufacturer where they were using water. You want to show all the areas where water comes into a process, but also where water goes out of a process, because this will help you identify any losses within the system. And then the color coding on this is representative of different types of water. So we'll have one color for city water, another for treated water, such as reverse osmosis, and we could have another color for wastewater. So you just kind of keep everything, you want to just make it as clear as you can with those color coding and the arrows showing the direction of water. So to have a helpful water balance, you need to include every water using process at the facility. If you leave some out, then you're going to be missing opportunities where there could be saving. If you are at a manufacturing facility, it's okay to group all domestic uses together. You don't need to, say, have a separate box for showers and another one for toilets. You can just lump those all together. You want to show the flow rate in and out, because this helps you identify water losses. And whenever possible, use metered data. But if that's not possible, estimates are your next best option. And you should show any return flows as well. So if water comes out of one system and then is used by the same system again or another system, you should show that on your water balance. So for the event itself, on the first day, you want to do a facility tour. So you can sort of train everybody in the group on where water is being used, and you can go look at the processes so that you see it in person and you can visually identify anything that might be sort of off. And then the first day or two, everybody should be throwing out just straw man ideas, get a general brainstorming going. And over the next day or two, you can make more measurements where they're needed, where you don't have the data that you want, and refine your straw man ideas into more defined opportunities. So I'm sure everybody has heard reduce, reuse, and recycle before. And this is where we generally start when we're looking at a facility. So step number one is to look for places where we can reduce water flow. Lots of times systems are set up and then maybe forgotten about. So people might not realize that the demand on water in a certain part of the facility has gone down. And so water's still flowing at the full flow rate, but we don't need that anymore. Or maybe over time that flow has increased for some reason and we need to just go back and turn it down. And these are the cheapest options, the lowest hanging fruit, and those are the ones you want to identify first. So once you go through that, you can look for opportunities to reuse water. So maybe you have a process such as reverse osmosis that's rejecting a lot of water. You can probably take that water reject and use it for another system in your plant that's a little less sensitive to water quality. And then the final area where we look are places where we can recycle. And the reason why this is last is because it tends to be the most expensive. So this can create lots of opportunities in your plant, but it probably involves some capital investment when it comes to treating the water. The 5 whys are a component of Six Sigma, and this is a process to get to the root cause of a problem. So this example here is a non-contact cooling water system that had a very high flow. And we go to the plant and we ask, why is this flow very high? And an operator might just tell us, well, it's high because the hydraulic cylinder gets really hot. And they might think that's the end of it. The cylinder's hot, so we need this much water going to it. But if you ask why again, well, the oil is over temperature. Why is the oil over temperature? The heat exchanger is not running efficiently. Now we know that if the heat exchanger is sized for the equipment that it's using, it's properly sized, there's no reason why it shouldn't be running efficiently if it's not broken somehow. So we want to ask, why is the heat exchanger not running efficiently? And then we hear there's scale buildup on the non-contact cooling water side of the exchanger. Scale buildup is caused by hot water. So then once we get to this root cause and we realize that the water is hard, we can think of some solutions that might help us reduce this flow. So maybe we can do water softening before the non-contact cooling water enters the system, or we can implement some sort of maintenance scheme where the heat exchanger is cleaned out every couple months and we get rid of that scale. Then that allows us to reduce the flow here and save money. The cylinder doesn't need to get as hot. Our equipment lasts a little longer. It's all good things. So here are some common opportunities at manufacturing sites especially to save water and in the process save energy. I won't go through all of them, but we can touch on cooling waters here. One of the things we talk about is the number of cycles. So sometimes cooling towers are set up so that they always blow down after the same number of cycles, but during a water Kaizen Blitz event, we can go in and test the water to see if it's actually needing blowdown at the point where we're doing blowdown. There's a chance that we're blowing down when that water is still fine for a few more cycles, so we can increase the number of cycles. Common places that we want to look are, we want to compare the actual flow to the required flow. We want to compare delta T anywhere where water is being used for heat exchange. We want to make sure that water is only flowing when it's needed. Sometimes in manufacturing processes, water is going to a system 24/7, but people are only using it 16 hours of the day. So we want to identify situations like that where we can easily reduce some of this waste. And then after the Water Kaizen Blitz event, we will write up a report with all our findings, and then we need to validate the concepts that we've come up with. We need to validate costs. We need to secure funding and secure engineering support. So get everybody on board with these. Sometimes these events don't move forward because people say, oh, well, water's cheap, we don't need to do that. So that's why it's important to document the total cost of water so that you can go to your facilities manager, go to the owner and tell them, look, this really is a bigger deal than it appears at first. So obviously, as with anything in life, if you prepare for an event, it'll go better. So to have a successful Water Kaizen Blitz event, you need to have thoughtful preparation. Good water balance is important since this will identify all the areas in your facility that you can look at to potentially save water and energy. If you have somebody who has done one of these events, that helps, but it's not necessarily a requirement. You definitely need people who know about the processes at the site and know how the equipment should be run, how it's actually running, and if anything is sort of out of whack, you want to hear about that. So once again, diverse teams help with this. Those get you the creativity that you want, as well as the knowledge of all the different processes. If you have any tools such as modeling tools that can quickly show you what the effect of changing set points in the system or any other values would be, then those will help. And good support from management is important since that's how you get access to all the places at the site that you want to see and how you get the information that you need. So I'm going to walk through a few case studies, and I do have to preface this with a statement that I wasn't directly involved in any of these. They were done by my coworkers, so this is the area where I'm going to try my best to answer everybody's questions, but if I don't have the answer, I know exactly who to ask for it, so I will get you those. This first one was at a manufacturing facility. They had 5 water-sealed pumps that each had a flow of 4 gallons per minute cycling once through. So that meant 20 gallons per minute were just used to seal these pumps and then immediately sent to the wastewater treatment plant. And when we came in to do a water balance and look for areas where things could be improved, one of the facility managers had actually heard about a kit that could convert these pumps into oil-sealed pumps. And once the pumps were converted over, they had better vacuum seals and they ran more efficiently. So we saved 20 gallons per minute of water and actually improved the equipment that was available at the site. So total savings came out to 10 million gallons per year, which is a huge amount. And they saved $106,000 per year for a return on investment of just over 1 year. So that was a pretty quick success. This was at an automotive facility. They have a paint shop to paint all the cars before they leave to be sold, but a lot of prep has to go in before you can paint a car. They need to be scrubbed and rinsed, pressure washed, and it takes a lot of water. So this facility had 2 lines to wash the cars, but they only had enough production to run one of the lines full time. And the other line was only ran for 1 shift, so 8 hours of the day. They were using reverse osmosis for the water to rinse these cars, and there was one supply line that went to both of these rinsing lines. So when they went in and did the water balance, they found that while both rinse lines were running, the flow out of each of them was 73 gallons per minute. But when only paint line 1 was in use for 2 shifts of the day, it wasn't all the way down at 73 gallons per minute. It was actually running 103 gallons per minute because just hydraulically, the way that the water was splitting. So they thought about that, and clearly 73 gallons per minute was perfectly fine for the shift when both lines were running. And they came back and created standard operating procedures to tell the employees that we can just run 73 gallons per minute during all 3 shifts, no matter how many lines are in use. So they installed pressure regulating valves to help with this. And then with just those 2 fixes, they were able to save $130,000 per year, which was 14 million gallons of water. And this one had a return on investment of just a couple months because all they needed to do was put in a valve and write some standard operating procedures. So this is my last one. It was a facility that wanted to increase production, but they were limited in how much water they were allowed to use. They weren't able to buy any more water from the city. So looking at their process, they realized that if they wanted to increase production, they were going to have to reuse water on the site. And they had a problem because the water coming out of their wastewater treatment plant had a lot of hardness to it, a lot of salts in it. So at first they were thinking they needed to put in this membrane facility, do some reverse osmosis to be able to reuse that water because they had to remove all the salts. But then they went through the 5 whys of asking, why is this water so hard? And they realized that the cooling tower blowdown and the softener regenerate were really the 2 only really hard water processes coming through this plant. So instead of building the membrane facility, they just sent the blowdown and the regenerate out of the system, and they took the rest of the water, put it through the on-site wastewater treatment plant, and that was enough purification for them to reuse that water again. So with that realization, they were able to avoid the capital cost of putting in a membrane facility, and they also saved 10 million gallons per year, basically not really doing anything different, but rejecting some of the water that they had previously been treating. And that was all they needed to do. Okay, so hopefully you learned a little bit today about how much water is required for energy use and how much energy is required for water production and endpoint use. And hopefully you have some ideas for how you could go to your facility and potentially save some water. But since we saw how much water energy needs to be made, even if you're not saving water, as long as you save energy, you are saving water off-site. So these are very connected systems, and any savings in one is also a savings in the other.